It's free energy. He basically goes and collects manure from the cows and feeds it in. He doesn't need to buy fertilizers in the same way as before, and it also gets rid of another problem, which is your livestock waste. We haven't put his sewage in there because he's in the municipal area, but if you put sewage in there, human sewage, if you expose it to anaerobic conditions for a certain time and the temperature gets up, you basically kill all the pathogens. So it is a way of sterilizing sewage and therefore reducing health risks. Now, we have been putting biogas digesters in the community to understand what the technical issues are, where do they work, when don't they work, what are the social problems, the social issues, what are people's concerns, and sort of trying to monitor to understand what the problems are. And here is an example of one of the first one, in fact, on that farm we were putting in. The students dug the hole, they did the bricklaying, and basically this is the balloon before it's blown up in there. The one side, as I say, is you feed in the manure, and the other side it comes out, it's got no smell, and it goes straight onto the field from there. We've been working with our Engineers Without Borders chapter, who've been very spearheading these implementation of these digesters. And the first one we put up at Mulder's Drift, it's been going now for 3 years. The farmer uses about a half a bucket of manure every second day. He cooks for 4 hours, and he does his lighting with that. And he really hasn't had a problem. It goes through summer and winter. There's a picture in the background of the bag blown up. If the pressure goes a bit low, you just throw a tire or two onto the bag. That's your pressure regulator. So it increases the pressure and you just get a higher flow of gas. How we actually identified him is when we first started at UNISA, and our students doing this work had to look for sewage, not sewage, manure. And I challenge any of you to try and buy manure that's organic and fairly fresh on a procurement system. See who the approved vendor is. So eventually the students in desperation went round with buckets to Mulder's Drift, which is quite close to our campus, knocking on door to door and asking if they could get donations of manure. And this farmer was so intrigued, he wanted to know what, and the students kept going back to him. And he couldn't believe this, and that's why we tried him as a test case. And what is interesting now, his neighbors are all very interested and all want one. And so I think, you can actually spread this organically. We also have one at our Lenasia site, and what's interesting, the security guards, the gardeners, all now want to put one in at their home, which is, in their sort of rural area where they're coming from. And they all use it for cooking and their showering and so on. So it does sort of work, and the people using it seem to be quite, find it easy to use. Further places we've put in lots. I haven't given a complete list here. There was a joint project with SNERD and the University of Fort Hare, and then our Institute of Corporate Citizenship to put digesters in the Eastern Cape. And we're now putting in 20 small digesters in Gauteng because it'll be easier for us to monitor. And this is funded by SNERD and Exaro, and the first one is in, and we're about to get one of the vice principals to come and cut the ribbon and light the stove and so on. And so we're looking at different sites, as I say, with an idea to understand where they work and where they don't work. But we've also taken the research, apart from the lab where we're there, looking at different types of manure and so on, but looking at the business case. And what could one do in informal settlements? And we're working with an overseas company. They're from Sweden, and they actually manufacture toilets for refugee camps. They supply them to the United Nations and to the Red Cross. And they're quite keen to see if they could use biodigesters in these situations, that they could at least get rid of the waste or sterilize it, and also then produce energy which could perhaps be used in the kitchens or for lighting the refugee camps and so on. But they're also keen to spread it further, which is why we're looking with them at seeing at an informal settlement site. And what we would like to do is see if we could use sewage as some of the feed or all of the feed in this biogas system. And depending on we're looking at various models. We could either feed to households or public facilities such as clinics and schools. If you're looking at households, then you actually need farms because humans don't make enough waste to power their energy needs. So you would need places where there's manure available. If you're looking at just using human sewage, then the gas is enough to supply to schools, clinics and so on, but not to the households. So we've looked at both cases. And where we've been looking particularly is at Joe Slovo, because that's one of the communities that our Institute of the Social Scientists work. And here's an aerial picture of Joe Slovo, and what makes it very interesting is it has got farms around it, and there are lots of cows and manure available around the site. And so we've been working with the community and the school kids and the schools in the community to try and understand what they want. Because the other thing is, if you're going into a community, what do they want with toilets? I mean, I can't go in and put in a toilet and say, well, you know, well done. You have to understand, what are their concerns? Do they want it on the house, next to the house? How would they like it? You know, it's very strange. Research, in a way. I was once phoned by the dean saying, where are you? I'm missing a meeting. And he says, I'm going around the settlement and we're going looking in toilet by toilet. And I'm sorry. But you have to talk to people and understand what they've got, what they want, what their concerns are. You know, you can't ever go into communities, decide what they need, put it in, and then hope it's going to work. You have to get their buy-in at all stages. The kind of system, and this is the loose toilets like they use at refugee camps, but these could be modified perhaps to bolt onto a house if people want them bolted onto their house. Safety is an issue, people going out at night, but you know, one would have to look. These toilets work on a cartridge system, and they basically empty under vacuum. And why there's an advantage to this is that when you have a system like this, you're not mixing other sources of wastewater with the sewage. Because often if you look at sewage that comes out of sewage works, there's all sorts of heavy metals and stuff. In other words, it's been contaminated by off-runs from industry, wastewater from other sources, and so it's not really suitable as a fertilizer. If you can just use waste, human waste and animal waste, it is much easier to use that material than as a fertilizer and a soil enhancer, because you don't have all the build-up of these other kind of problems. Also, if you're using this kind of system, you don't have to put in running water, and you don't have all those other problems. The concept would be that there would be a system set up of cartridge removal, and then these cartridges would be sent to a central site. The proposed pilot at the moment, because the company also hasn't got endless funds, is 20 houses, perhaps they're in Thembelihle, and we've been looking at the gas flows and the piping layouts and so on, and how one would collect sewage from the households, because the access to the households is quite complicated. So you would have to actually use trolleys and manpower, and therefore you have to limit the size of these cartridges and so on. This would be one of the layouts, and this is maybe the first 20 houses, and then there would be an adjacent, on the farmer's land, a biogas facility, which we would supplement the feed from the cartridges with manure. And with this system, we could supply 2 to 3 hours of gas per day to each household. Now, the basis, when we did our business case, is currently the municipality, it costs an awful lot of money for them to empty pit latrines. And then they have to take that waste to some distant site to be treated. If we could keep the same subsidy for this system, so that would be one of the incomes, and the main product is the fertilizer. As I say, the gas is the smaller cost, so that you could actually supply free to houses, but supplying free to social scientists, that always lead to other problems because, you know, but anyway, so it's an interesting thing when you're working on these projects. But what is interesting, with this basis like that, you can create 6 jobs, paying at 5,000 to 6,000 Rand a month for these 20 households, which means about a quarter of the households get a job. Or if you wanted to make them half-day jobs, each household could get some source of income. And the payback period's about 5 years. You know, and so then you have a system where you're actually creating jobs, you're removing a problem, and you're supplying energy. But you know, this would have to be done with community, with local, the local authorities, and we'd have to do this very carefully and see how it works. So there really are opportunities, and we've done other business cases where we've looked at just using sewage and supplying hospitals and clinics. Also looks pretty good, the economics. As I say, and the big thing to me is one can actually create jobs, and it's the community helping themselves, which I think always works much better than trying to do things for a community. You know, work with the community, let them help themselves. Looking at the other waste, to go on dry waste. Plastics are a fantastic source of energy and a real problem environmentally, for example, but any other material that contains carbon are all potential sources of energy. Tires, they're not the ideal, but they've got lots of energy. They are a little bit more messy to work with than plastic. And what we've been looking at, we go through the gasification route, and then from there you can go to various products. So if we look at converting dry waste to energy, as I say, we would typically use high temperature, where you basically heat up the material with too little oxygen so you don't burn it. You basically react it and convert it to CO and hydrogen, and carbon monoxide and hydrogen are the workhorse of the chemical industry. Once you've got that gas, it's much easier to work with. You can convert it to electricity if you wanted to. And as a rule of thumb, and it varies, plastics more, other waste, if it's very wet, less so. But basically a ton of waste per hour would produce you about 2 megawatts of electricity. You could go to fuel if you wanted to via an XTL process, and I'll talk a little bit more about that. And on that basis, about 1 ton of waste produces about 1 barrel of synthetic crude. So that's a mini Sasol process. And the product coming out would be the same as a Sasol process. And the other byproduct is heat. If you go from even a coal to electricity plant, 40% of your energy value goes into electricity, 60% goes into heat, which is what you see going out those big cooling towers. An advantage of small plants in and around a community is that waste heat now becomes a resource. That waste heat can be used to heat up the water for the community, supply space heating. If there's an industry nearby, it can supply its heat. And so what you can do is, even though your plant is maybe less efficient than a big equivalent ESCOM or a big power station, because you're using the heat, you can push up your efficiency to 80%, fairly easily. And that is a huge advantage because you're basically using all that energy value in the material. And so you could have a system where there's the gasification unit, and you could supply a household or a company, industry with electricity. You could supply it with waste heat, and you could do fuel. So there's and when you combine the system and look at integrated, and I suppose what we're proposing here are distributed systems. That people become more and more sort of responsible for their own energy needs, and they integrate what they require with the technology. As I say, you can actually get fairly cost-effective solutions. The kind of waste you're looking at is about 10 kilograms an hour, which doesn't sound a lot, but if you're collecting it by hand, it is actually quite a bit when you're looking at that sort of value. Say for a farm, to supply a farm would be 10 kilograms an hour. Now the XTL that I was talking about, X means converting something to liquids. So CTL, for example, is the Sasol process in Secunda. GTL uses gas to liquids, and BTL uses biomass to liquids. And these are all different carbon sources that go through the gasification process, go through a chemical process, and from that you can get fuels, and you can get chemicals which are actually higher value than the fuels. And in particular, the waxes, the lubrication oils, and so on. The Fischer-Tropsch products make extremely good lubricants, it's a very good chemical feedstock. And you can vary what you get by changing the catalyst. Iron-based catalysts, which are what we've been tending to use because they're cheap, are lighter products, and cobalt catalysts typically make medium to heavier products. But you don't need to just use biomass only in the classical sense. You can basically use any waste that contains carbon. So we have an Australian group that's looking at waste residue oil. Waste plastic is fantastic. It really is an incredible resource. It's one of the nicest ones to use. Biomass certainly, but it's wood chips and stranded gas reserves. In Nigeria, there's an awful lot of wasted gas that just gets flared. It's actually a crime against future generations. But the problem is it's too small for the big guys to go in. But if you could build smaller plants, you could actually use all of that kind of waste. And so you take your feedstock and you turn it into products, and there's the waste heat. And if you wanted, you can also co-produce electricity. So the system we've been designing and working with is and then when you start working with these products, whether you're gasifying or reforming, it becomes quite an interesting thing, because you've got to balance how much oxygen and steam you use depending on the source. And sometimes it's even more pyrolysis. It's not a sort of 3 separate boxes anymore. It's a joint. You've got to be a little bit more creative. Gas cleanup, the Fischer-Tropsch, and then the separation into what the products you want. Is this a pipe dream? No, we built a biomass to liquids pilot plant. It was air-blown with a downdraft biomass gasification. We had syngas conditioning, and we had Fischer-Tropsch synthesis, and it was produced a half a litre a day of capacity, and this was commissioned in 2012 in China. It was jointly funded by the NRF and their equivalent MOST. And that was wax we produced. It was a very, very, very high quality wax we made from this little facility, and that wax started off as wood chips. We're working with small-scale gasifiers. We work with Nexa, and that's one of their plasma gasifiers. It's very high capacity. That tiny little thing over there can treat up to a ton a day. It really is. They're very small and they're very robust. And we're working with them to modify that. We actually do a mixture between electrical gasification and adding in oxidizing sources. We've also built our own fixed bed gasifiers. This I always laugh at because our first one started off as drums, 44-gallon drums, and we still use them. And then we got the mechanical engineers involved who started designing, and I now call this guy Fat Boy. But the reason he turned from a 44-gallon drum into something like that is the company had spare steel available, and so it ended up with, you know, flanges like this and whatever instead of the 44-gallon drum. But Fat Boy has been set up that we can actually it's quite versatile. We can move the combustion zones and so on. So it is basically a research facility as well. It can be disassembled and reassembled and changing the configuration, which the 44-gallon drums was a little bit harder to do. We have a fantastic facility out at Nexa. We rented a building from them, and we actually use their workshops, and we fall under their safety management systems, which is great. What we have put in is we got at the bottom here is the classical FT lab sorts of things, the little reactors where we can test catalysts and do our development and so on. We've got all the analytical equipment we need. We've got a really state-of-the-art GC that was built for us. One reading, which used to take us about 3 days to get, now takes us 20 minutes. But what's exciting is we're actually building a pilot plant where we can actually link the gasifiers to reactors with a gas cleanup system, and this is our reactor. And that's the top of it. You have ladders to get to the top of it and so on. So they're full-scale tubes where we can actually test. And we're developing our own catalyst because we're looking, one of the major costs of these are catalysts, and we're developing our own low-cost catalyst that we can get our cost down to from sort of $1,000 or $10,000 a ton down to $50 a ton. And it's actually working quite nicely. Is this a pipe dream or not? Let's see if technology works. I just want to show you this. Let me put the volume up. This is our everyday world. And this is where it all ends up. The consequence? Polluting the environment and sterilizing the land. Globally, 140 billion tons of biomass waste and 2 billion tons of garbage are produced every year. From this, we could produce 100 billion barrels of green crude oil. As South African engineers, we are passionate, uniquely qualified, and we have a solution. Using our technology, we've built plants in China and Australia. We have designed a container-sized plant to convert waste into green crude oil, which can be used in cities and in rural environments. Our motto, for Earth renewal, use waste as fuel. And yes, we can do it, and together we can change the world. And, you know, just from the waste that's available, we could replace twice the oil consumption of the Earth. And solving then problems, I mean, that waste basically eventually goes to greenhouse gases without us recovering the energy. So we're not talking about taking food from people, we're talking about just taking waste. It is a huge resource, but we've got to think differently. Governments have to think differently, society has to think differently. Cost-wise, we come in even on the small plants. Our first one, it sort of costs similar to the big plants, and if you make many of them, you obviously can bring the costs right down. And some of our partners are looking at costs that make us gulp, but they say it's quite possible because they know what it went from in the computer industry. You know, it's the same thing if you build one computer or you're building many of them. If you can think of this as a process where you're going to, you know, rather than building each plant one by one, you kind of supply the user with a plant that they can customize, like your PC. You decide what software you want to add on to it. You can bring costs right down that it really is economical. So, sorry, there we go. Let's see if we can get to the next one. What am I doing? Oh, there we go, right. But I think what we're looking at when we're looking at waste is it's a paradigm shift. We have to make small processes. This is not your Eskom. Eskom can't think small. It's probably not your Sassels in the classical sense. They can't think small. You're looking at new companies that think small, think differently. You're looking at waste as a resource. You need to think differently about it, not how you're going to stockpile it, but how you're going to get it and where you're going to use it. You're looking at making your fuel, electricity and your heat from these as a resource, and how do you do that efficiently? But what becomes different is it's got to be socially acceptable. The Escoms and the big factories, they kind of have to do some sort of social thing, but it's just for the people around them usually. This we have to work with people to understand what their needs are, what their concerns are, how do we work with them. We've got to look at the environmentally friendly because it's smaller. These plants are not wouldn't be run by chemical engineers, so you've got to build them that they're more inherently safe and friendly. We've got to go for efficiency, but robustness. They've got to be simple because the operators are not high-tech people. You've got to make it really, really simple and cheap. And this is really what we're looking at. And I think it's an interesting and exciting thing. I think we've got a great team, but I think we need a lot more people in on this. But there really is, I think, a way we can benefit Africa and the developing world by taking this waste, supplying energy, and I think what's important in this context, supplying jobs as well. Thank you very, very much.